Electron affinity can be thought of as an opposite of ionization energy. Now, instead of removing an electron, we want to add an electron to the atom. We are hence looking at the amount of energy released to introduce this electron to the valence shell of the atom. The general trend is that the electron affinity increases across the period, meaning that more energy is released. This makes sense since effective nuclear charge increases across the period, meaning that an additional electron would feel a greater attraction force from the nucleus and hence a greater tendency to be added to the valence shell. Halogens of group 7 particularly have a very high electron affinity. The addition of one additional electron results in a very stable octet configuration. Once again, we do see some deviations here. The first is at group 2, the second at group 5, and the third at group 8. At these three positions, the electron affinity is lower than it should be according to the trend. In the case of group 8, it is quite straightforward in that the outermost shell is already full. Any more addition of electron would go to the next shell instead, which requires energy to keep it in place rather than releasing it. The reasoning is very similar for group 2 in the sense that the S subshell is already completely full and the next electron will be added to the P subshell, which is of a higher energy level. As for group 5, the energy required to add the electron mainly comes from the repulsion. Recall that in each p orbital there is already one electron, and adding another electron into this orbital will result in some slight repulsion and hence a drop in electron affinity. Now, down the group, the electron would be added to an outermost shell with a larger n, which is of a higher energy level. As a result, less energy will be released, explaining why electron affinity decreases down the group.